The standard equation taught in every high school physics classroom is F equals ma, force equals mass times acceleration. It is an effective approximation for introductory problems, but it is mathematically incomplete. Students and entry-level engineers rely on this formula because in low-energy terrestrial environments, objects generally maintain a constant mass as they move. In these specific cases, the approximation holds. But aerospace applications, like the Space Shuttle Atlantis, represent a high-stakes environment where mass is not constant. To reach orbit, the vehicle must expel millions of pounds of fuel in minutes. Its mass is a rapidly changing variable, making any algebraic assumption of a fixed constant useless. If an engineer attempts to calculate the launch trajectory by plugging a shifting mass into F equals ma, the math fails to account for the momentum of the lost fuel. The resulting error leads to a total mechanical collapse of the flight profile. The rigorous calculus-based formulation of Newton's second law defines force as the time derivative of momentum. Force equals dp over dt. We are going to set aside the algebraic simplifications and rebuild classical mechanics using the framework of differential calculus. Mastering the derivative of momentum provides the mathematical tools necessary to calculate the behavior of variable mass systems and high-energy trajectories. Classical momentum is the exact product of an object's mass and its velocity. Velocity describes the motion, but the momentum calculation requires us to account for the total quantity of matter that is currently moving. When we apply the time derivative operator to momentum, a standard product rule expansion yields mass times acceleration plus velocity times the rate of change in mass. While this expansion is mathematically valid for many functions, applying it blindly to physical objects creates a calculation error. Newton's laws strictly govern a fixed, unchanging set of particles. A single object that continuously loses mass as it moves violates this fundamental boundary. In our rocket example, the exhaust gas being ejected from the engine bell represents mass leaving the vehicle's boundary. This ejected matter still exists and carries its own momentum away. We resolve this using a control volume approach. By tracking total momentum and subtracting the momentum of the ejected gas, we maintain the system's integrity. This differential method allows us to track both the accelerating rocket and its exhaust plume as a single conserved system of matter. A precise definition of force requires us to establish an absolute mathematical boundary around every individual particle involved in the interaction. These boundaries become even more critical when we analyze the mechanics of collisions between multiple bodies. Newton's third law is often taught as a behavioral observation, that for every action there is a reaction. Consider a theoretical thought experiment. Two metallic spheres in a perfectly closed system, isolated from all outside interference. Before they collide, each sphere is assigned a specific momentum vector, p1 and p2. The time derivative of these vectors gives us the exact forces acting on the spheres during the collision, F1 and F2. In an isolated system, the total momentum remains constant throughout the interaction. Because the total momentum is constant, the rate of change for the entire system must be zero. For the total change to be zero, the derivative vectors of the two bodies must be equal in magnitude and point in exactly opposite directions. Newton's third law is the direct mathematical result of an unbreakable symmetry, the conservation of momentum in a closed system. However, this model of instantaneous symmetry fails when applied to moving charged particles. On the subatomic scale, particles interact across empty space via electric and magnetic fields. These interactions are governed by the Lorentz force, which defines exactly how fields exert momentum on charged matter. In this scenario, two moving charges interact magnetically, curving their paths as they move through the void. We must now account for a relativistic constraint. No signal or force can travel faster than the speed of light. This speed limit introduces a time delay. When particle A moves, its field takes time to reach and affect particle B. During that specific interval, the momentum of the particles alone does not sum to zero. To resolve this, physicists use the Poynting vector, which assigns momentum directly to the invisible electromagnetic field. The field itself absorbs the missing momentum and carries it across the vacuum until it interacts with the second particle. This means that to satisfy the law of conservation, we must accept that empty space is a physical participant capable of carrying and storing momentum. Modern mechanics remains rooted in Isaac Newton's monumental mathematical achievement. His three laws are parts of a unified architecture, describing how matter moves within inertial frames. However, in physical systems with complex constraints or chaotic motion, a vector-based approach becomes computationally impossible to manage. Because energy is a scalar quantity, a single value without a direction, it allows us to calculate the state of a system without resolving the thousands of individual force vectors involved in the chaos. This leads to the Hamiltonian formulation, a tool that uses momentum and position to track the total energy of a system over time. The mathematician Emmy Noether proved that the conservation of momentum used in these energy models is a direct result of spatial symmetry. This momentum-based framework allows us to map the mechanics of planetary orbits and celestial systems with extreme precision. It is equally vital for analyzing complex nonlinear terrestrial systems, such as the intricate equations of fluid dynamics. This reliance on momentum even extends to the subatomic scale through the quantum Ehrenfest theorem. Advanced physics relies on this rigorous accounting of momentum to define the behavior of the physical world.